start recording here. There we go. Recording started. Good. So yeah, Secret Canada is NGN is happy to host this technical webinar on offshore grid forming control in parallel VSC HVDC bipole systems by Riley St. Hilaire. I just found out that the ST stands for Saints, so you'll be getting a technical introduction and a blessing as well. It's going to be good. So yeah, so a quick bio on Riley. Riley is a power systems specialist working in consulting and is a part-time graduate student. He has over 5 years of experience with analysis and modeling of power systems in industry and academia. He has been working with Transgrid Solutions since 2020 as a studies engineer, and prior to which he worked with Manitoba Hydro in the System Performance Department with operations. He's working towards his master's degree in electrical engineering, and his research interests include offshore grid forming control and offshore grid stability. He has experience with EMT and RMS modeling and dynamic performance evaluation of VSC HVDC systems, renewable generation, including wind, PV, BESS, and FACTS devices. So with that being said, I will hand it off to Riley, who'll do his presentation. And if you have any questions, please save it for the end. You can either post it on the chat or we can unmute you and you can ask your questions to Riley. So yeah, thanks, Riley. I'll hand it off to you.
Hey, thanks a lot, Kassin. For the introduction, hello, everyone. First, let's make sure you can hear me. Sid, can you just make sure that, let me know if you can hear me. Make sure we have the title slide that you guys can see that as well.
Yeah, I think we're all good on that. Yes.
Perfect. All right. Thanks for attending this webinar. It's great to have this opportunity to present to our NGN group. Hopefully you guys find this somewhat interesting and can take something away from this. As Kassin had mentioned, I was lucky enough to get the NGN sponsorship, so I was able to present this work at the last Paris session in 2022. The sponsorship is a great program, and I would encourage any NGN members to submit a paper based on their work, either in industry or in academics. You'll get the opportunity to present your work at your respective study committee group discussion meeting and have the chance to meet a lot of like-minded people. As far as I can remember, the call for papers is near the end of the year, so you can keep an eye out for that. So the work I'll be presenting today is the same as was presented in Paris, but since we have a bit of longer time, it will be the expanded version. First, we'll take a look at what the project overview. We'll briefly discuss what a grid forming converter is and what it isn't. We'll take a look at some of the principles of grid forming control. We'll look at some of its challenges with respect to offshore HVDC systems, present the grid forming control concept that was used in this study. We'll take a look at the test system that was used to test this controller. We'll look at some EMT simulation results, review some of the cons of the proposed controller, go over a summary of the study, and finally talk about some of the future work in this area. So first, just an overview of the North Sea Wind Power Hub project. This work was done at TGS for the NSWPH. It was a partnership between Tenant, Energenet, and Gasunie. And the project is also co-financed by the European Union through the Connecting Europe facility. The 2 reports that TGS wrote for this study have been made public, and you can find them at this link here. Most of the figures in this presentation will come from these reports. The purpose of the study was to look at the technical feasibility of an offshore wind collector system in a hub and spoke topology. In this topology, the wind generation is collected through low voltage AC cables to a common location, which is considered the hub, and then transmitted to various onshore sites through HVDC links, which form the spokes. The study compares 2 offshore topologies. there's a DC coupled topology and an AC coupled topology. You can see in the DC coupled topology that there's a common DC node to which the HVDC links are coupled at the offshore side. And the AC side is isolated where each individual pole is fed by a separate wind park. For the AC coupled topology, the common node is on the AC side of the offshore converters. So all the wind and offshore converters are connected to the same high voltage bus, the 400 kV bus. In both topologies, the offshore HVDC converters form the AC grid, while the wind generation is in grid following mode. So the focus of this presentation will be mainly on the AC coupled hub topology, which is the one on the right there. So first, I think it's important to take a look at what a grid forming converter is exactly, so we can agree on our definitions before moving into the details of the study. The CGRE Study Committee B4, which is the DC and Power Electronics group, formed a task force, TF77, which published the definition for a grid forming converter back in 2019. Let's take a look at this definition and we can break it down a little bit. First, a grid following converter is one that matches the AC grid voltage and frequency, usually by a PLL, and can provide reactive current equal to the steady state rated current during AC faults. A grid forming converter, on the other hand, regulates both instantaneous AC frequency and AC voltage. Such a converter is also able to provide reactive current equal to the steady state rated current during AC faults. So the fault current portion is no different. The key difference here is that a grid forming converter regulates AC voltage and frequency. Now, a question that I have at this point is, can't a grid following converter also regulate AC voltage and frequency? So if the inverter has a voltage dependent reactive power response and a frequency dependent active power response, doesn't that mean that it regulates the AC voltage and frequency? Maybe it would be better to say that the grid forming converter is one that can generate rather than regulate the AC voltage and frequency. I think a good way to look at this is to ask the question, can the converter be used to black start the system? If the answer is yes, then it would be a grid forming converter. Otherwise, it's grid following. Now, a synchronous grid forming converter, according to this definition, is a grid forming converter that is also able to operate in parallel with other AC frequency regulating equipment. So if you only have one grid forming converter, which is operating in an island, it doesn't have to be synchronous because there is nothing for it to synchronize to. This makes intuitive sense. Lastly, we have the virtual synchronous machine, which is a synchronous grid forming converter with energy storage capable of delivering additional energy for a short period of time from the converter rather than the DC link, and rated to provide a current greater than the steady state rated current during a fault. So the key here is that the converter must have energy storage capability and be capable of delivering additional energy over a short period of time. Also, the fault current is greater than steady state rated. The quantity of additional energy and the time frame, which are not specified, so this is somewhat vague. I'm not sure why they have specified that the energy must come from the converter rather than the DC link. From the AC system perspective, which is the perspective that matters when we're talking about a converter that is regulating the AC voltage and frequency, why does it matter where the additional energy comes from? And what type of converter do we have if the energy comes from the DC link? Also, what type of converter do we have if there is no energy storage, but it provides fault current greater than steady state rated? So I do think there is some room for improvement or movement with these definitions, but at least it gives us a starting point. If we look at a Venn diagram of this definition, we have a grid following converter, which is mutually exclusive from a grid forming converter. Grid following converter matches AC voltage and frequency and can supply fault current equal to steady state rated. And the grid forming converter, on the other hand, can supply the same fault current but regulates the AC voltage and frequency. And then within the subset of grid-forming converters, we have synchronous grid-forming converters, which on top of regulating AC voltage and frequency and supplying rated fault current can operate in parallel with other frequency regulating equipment. And lastly, we have the virtual synchronous machine, which is a synchronous grid-forming converter, which has energy storage capability and supplies fault current greater than 1 per unit. So what type of converters do we have in the North Sea Wind Power Hub? Just by considering the hub topology, we can say that the DC coupled hub must have a grid forming converter. It regulates the AC voltage and frequency, but it is isolated, or sometimes we call this islanded mode. Thus, it does not need to operate in parallel with other frequency regulating equipment. For the AC coupled hub, if we consider that all HVDC converters must play a role in the offshore frequency regulation, we must have a synchronous grid forming converter because it must regulate AC voltage and frequency while also operating in parallel with other frequency regulating devices. Whether the offshore HVDC converters can be considered a VSM seems somewhat vague because the energy storage capability from the converter itself is limited to the submodule capacitance. Energy can come from the DC link. However, as we saw, this doesn't qualify for VSM. Also, the converter can supply fault current greater than steady state. So if we relate this back to our Venn diagram, the DC coupled hub would fall in the set of grid forming converter, and the AC coupled hub would fall in the set of synchronous grid forming converter, with a bit of a question mark as to whether it can be considered a VSM or not. So now that we have a definition for a grid forming converter, let's take a look at some of the fundamentals. As we saw, a grid forming converter regulates or generates the AC voltage and frequency. So the converter looks like a voltage source behind an impedance. The internal voltage E primed and the internal angle delta are generated by the grid forming controls. In contrast to this, a grid following converter generally regulates its power output to a given AC voltage and frequency. Thus, it acts like a current source behind an impedance. The main voltage source in traditional power systems is the synchronous machine. Therefore, it makes sense that most of the grid forming control strategies presented in the literature use synchronous machine theory. So just as a synchronous machine controls its terminal voltage through the exciter, the definition of internal voltage for the grid forming converter can be thought of as the synchronous machine field winding excitation. Also, the synchronous machine rotor angle position relative to the grid defines its active power output, and thus the internal angle of the grid forming converter can be thought of as a virtual rotor angle. For operation in parallel with other frequency regulating equipment, a droop-based governor is generally employed in synchronous machines, where the machine speed is allowed to deviate slightly to coordinate active power distribution between parallel units. Again, the same concept can be used in the grid forming converter as a virtual governor. So although we can use the same mathematics to control the grid forming converter, we must remember that a converter and a synchronous machine are physically extremely different devices. It is critical that these differences be carefully considered and accounted for. First is the current handling limitations of converters. Rather than IGBTs, synchronous machines simply have windings, thus they can withstand huge overcurrents. According to the same task force, that's 77, synchronous machines can have short circuit current of up to 6 per unit without equipment damage. This means the synchronous machine is extremely robust to overcurrent conditions. Typical short-term overcurrent ratings of HVDC converters is somewhere around 1.2 or 1.3 per unit. So although the grid forming converter is meant to behave like a voltage source, we must monitor and if necessary, limit their current output. And this limiting must be done very fast to protect the equipment. Also, when the converter goes into overcurrent and is limited, it has effectively turned into a current source and has lost its ability to regulate the AC voltage and frequency. This is a major consideration and has significant implications on transient stability. If we imagine the behaviors of a synchronous machine during a terminal fault, what happens? The energy entering the generator from the mechanical side continues at the same pre-fault rate. Although the machine is supplying current to the fault, there is zero voltage at the terminal, thus no power or energy exits the machine. This energy gets stored in the rotating mass of the rotor, causing the rotor to accelerate and the rotor angle to advance relative to the rest of the system. When the fault is cleared, the machine is no longer in synchronism with the rest of the grid. In order to resynchronize, the machine's rotor angle must fall back in line with the grid, and this process results in the excess energy stored in the rotor to be released by the machine and looks like a power swing. If the same dynamics are modeled in the grid-forming converter via the swing equation and synthetic inertia, it will attempt to behave in the same manner, where there is a post-fault power swing as the converter tries to synchronize with the system. So this figure shows 4 parallel grid-forming converters. They're smaller scale. These aren't HVDC converters, but they use the swing equation to generate the internal angle. You can see this post-fault power swing happening after the fault as the converters try to resynchronize with the system. Also, you can see the converter current getting pushed into the limit, which in this case is set to 1.3 per unit. In this example, the system remains stable, but if the power swing is too severe, the converters will not be able to resynchronize and the system will collapse. Another big consideration is the difference between the synchronous machine and converter impedance. Synchronous machines do not have a fixed impedance due to the induced currents in the field and damper windings, which decay at different rates. This is generally interpreted as a variation in the machine reactances for different time intervals, the steady state or synchronous impedance, transient and subtransient. The steady state impedance of a synchronous machine is somewhere around 1 per unit. In contrast, converters do not have windings and thus don't have induced currents. Therefore, their impedance is the same for all time intervals. For HVDC converters, this impedance is mainly coming from the converter transformer, so the impedance is around 0.1 or 0.15 per unit. Therefore, compared to the synchronous machine, the internal voltage source and controlled node are electrically very close for a grid-forming HVDC converter. This is nearly an order magnitude difference and has significant implications on interactions between parallel devices. So although synchronous machines are extremely robust, they're not perfect devices. If modeling the grid-forming converter using the same theory, similar issues with synchronous machines may arise. Firstly, there are electromechanical interactions between rotors, and this phenomenon is well known, and power system stabilizers are generally used to minimize them. The same phenomena can be seen if modeling a virtual rotor in a grid-forming controller. Also, there's the concept of the critical clearing time, where during a fault, the rotor angle advances far enough for the machine to slip a pole. Again, if modeling a virtual rotor in the grid-forming converter, they may suffer the same limitations to fault time. It's an interesting question. Can a grid-forming converter slip a pole? And if so, what does that mean? And does it have implications on the system stability? In summary to all this, synchronous machine theory is well studied, and the same mathematics can be applied to grid-forming converter control to generate the internal voltage magnitude and angle. However, we must always be cognizant that the two devices are physically very different. These differences should be carefully considered when designing the controller. Also, we should expect the same issues that are observed in synchronous machines to reappear in the grid-forming controller. However, grid-forming controllers should be more flexible in this regard because we can control its dynamics, whereas the synchronous machine dynamics are largely dictated by the physical parameters. Next, we'll take a look at grid-forming control, specifically in the context of offshore HVDC systems. Arguably, offshore systems present some of the most challenging conditions for grid-forming converters for a number of reasons. Due to the dominance of power electronic equipment, offshore grids have unique properties compared to their onshore counterparts. First, the converters are very tightly coupled. As we discussed previously, the impedance of the HVDC converter is about 10% that of a synchronous machine and much less than for traditional onshore IVR plants due to the absence of the collector system and the main transformer. In offshore HVDC systems, only the converter transformer impedance separates the converter from the point of common coupling. This has implications on steady state control interactions, which we will see a bit later. There's also almost zero inertia due to the lack of a rotating mass. Although wind turbines do have inertia, these dynamics are decoupled by the converter in a Type 4 system. This has implications on the rate of change of frequency and frequency nadir. Also, there is very little conventional loads in the offshore system which provide damping to transients. This requires a fast response from the HVDC converter to changes in the offshore voltage and frequency. VSC HVDC systems also require submodule capacitor energy balancing, and this can result in small errors between the requested voltage magnitude and angle from the grid forming controller and what is actually generated at the converter terminal. Although small, these errors could be large enough to cause interactions between the parallel converters. The offshore HVDC converters also require a high transient current limit in order to support the offshore system during faults. As we discussed previously, when the converter reaches its max current and the current is limited, the converter effectively turns into a current source and no longer has the ability to regulate the voltage and frequency. It is extremely important that the converter current reduces below the current rating and returns to normal operation as quickly as possible before losing the stability of the offshore grid. A high margin between nominal operation and the maximum current will help the converter return to regular operation faster. With all these challenges in mind, let's take a look at the control concept that was implemented in this study. The control scheme employs a fast master controller to coordinate the active power distribution between parallel bipoles by quickly modifying the converter's internal angle relative to the converter's frequency error. This master controller, which we call the offshore frequency regulator, calculates the error based on the converter's frequency droop, the error between the active power output and reference. The frequency error signal is then sent down to each individual pole level controller, which does the work to define the converter's internal voltage magnitude and angle. Also, additional control loops in the pole level controller are used to mitigate power oscillations and interactions between parallel HVDC converters. So let's take a quick look at how the master offshore frequency regulator works. First, we can calculate the resultant offshore frequency droop for n number of HVDC bipoles. We can also calculate the total power mismatch between the active power output and reference for each bipole. And then with these two quantities, we can calculate the expected offshore frequency deviation as the total power mismatch times the resultant frequency droop. Lastly, we can calculate the frequency error for each offshore converter, and this signal is then sent down to the pole level controls. The pole level controller defines the internal voltage magnitude and angle in the dq delta domain, then through a transformation generates the voltage references in the ABC domain. These voltage references are then sent to the switching logic to generate the desired voltage waveforms at the converter terminal. First, we'll look at the generation of internal angle delta. A frequency droop control is used to modulate the converter's frequency order based on the error between the active power output and the reference. This is a slow function akin to the governor action of a synchronous machine, which regulates the steady state frequency. This frequency order is then integrated to get the converter internal angle. The angle is modulated by the transient angle control loop, which is a fast controller used to regulate the converter's power output during transients. The frequency error signal is received from the master controller and divided by the converter's frequency droop to obtain the active power error as determined by the master controller. This is then compared against the active power reference and the actual converter output. the internal angle is quickly adjusted relative to the active power error using a PI controller to maintain the power balance. This is a major difference from the VSM swing characteristics, where instead of controlling the frequency, the internal angle is directly controlled. The AC voltage control is straightforward, where the measured terminal voltage is compared against the reference and the error is fed to a PI control, which adjusts the converter's D-axis voltage magnitude. Also, a reactive power droop is used to coordinate the burden of AC voltage regulation among the other offshore HVDC converters. The active power and reactive power circulation controllers are used to mitigate power circulation between the positive and negative poles of the same bipole. This controller forces the error to zero by modulating the D-axis voltage magnitude relative to the active power circulation and the Q-axis voltage magnitude relative to the reactive power circulation. These controllers resolve a steady state instability in the offshore system. The active and reactive power oscillation controllers damp out power oscillations coming from interactions between separate bipoles. The D-axis voltage is modulated relative to the converter's frequency error sent by the master controller, and the Q-axis voltage is modulated based on the converter's reactive current output. Lastly is the transient current limiter, which acts to lower the converter's internal voltage when the converter current reaches its limit. So if we consider this controller in the steady state, many of these additional control loops are not acting. The Q-axis voltage is zero, and the D-axis voltage is similar to the synchronous machine field winding voltage EFD, and is used to control the terminal voltage magnitude. The internal angle is similar to the synchronous machine rotor angle and is used to control the converter active power output. Now that we've looked at the control concept, let's look at the particular test system that was considered in the North Sea Wind Power Hub project. The system consists of two MMC VSC HVDC bipoles. Each are rated at 525 kV and 2 gigawatts with a 200-kilometer submarine cable. So this gives a total of 4 gigawatts of offshore to onshore transfer capability. The 4 HVDC converters and the 8 500-megawatt wind plants are all connected to the same 400 kV offshore PCC. The wind generation is connected through 10-kilometer 66 kV AC cables and a 3-winding step-up transformer. The onshore HVDC converters are operated in DC voltage control, and each HVDC link connects to an isolated Thevenin equivalent representing the onshore grid. So a detailed EMP model of the system was made in PSCAD and tested for small signal and large signal stability. One of the first issues we encountered was the presence of a small signal instability. This led to the addition of the active and reactive power oscillation controllers to mitigate this interaction. The figures at the bottom show the sensitivity to these control loops. The figure on the left shows the system with the active power oscillation controller disabled, and the figure on the right is with the reactive power oscillation controller disabled. In terms of fault ride-through performance, the controller works quite well. The plots on the left is for a bolted 100 millisecond three-phase to ground fault at the PCC, followed by a trip of 500 megawatts of wind generation. The disturbance results in the PCC voltage and converter power decaying to zero. At fault clearing, the HVDC system quickly provide the reactive power support necessary to recover the AC voltage and resume power transfer. The two HVDC bipoles work in a coordinated manner to recover the offshore grid following the disturbance. The power distribution among the HVDC converters is equal, even during the transients, and no swings in active power between the converters are observed. Therefore, the performance is much better than what is expected from a swing-based grid-forming controller, which would produce second-order swing dynamics. The post-fault power transfer is reduced to approximately 3,500 megawatts, and the frequency of the offshore system settles around 49.7 hertz. The offshore frequency regulator calculates the error in the offshore system frequency due to the loss of the wind generation. The frequency errors pass to the pole level grid forming controls, which reduce the amount of power absorption by roughly 125 megawatts apiece. The offshore power imbalance is distributed equally to the 4 offshore converters because the frequency droop is set equal at 5%. Note that the steady state error in frequency can be controlled within a tighter tolerance by reducing the frequency droop of the HVDC converters. The plots on the right is for a DC pole to ground fault on the positive pole of HVDC system 1 at the offshore end of the DC cable. The fault causes the offshore and onshore converters of HVDC system 1 positive pole to block, followed by AC breaker operation to isolate the faulty pole. During the fault, the faulty converter absorbs a significant amount of power while the healthy converters reduce their power absorption. Therefore, no significant excess power is absorbed by the wind plants. HVDC System 1 operates as a monopole with a DMR after the fault is cleared. With the trip of the positive pole, the offshore wind hub loses 1 gigawatt of transfer capability. To balance the power generation with the lower transfer capability, 1 gigawatts of wind generation is also cross-tripped with the delay of 100 milliseconds from fault inception. The healthy offshore converters increase the reactive power injection to the PCC to support the voltage during the fault. The reactive power injection by the 3 healthy converters flows to the short circuit through the freewheeling diodes of the block converter, resulting in very high reactive power absorption by the faulty converter. The voltage quickly recovers after the faulted pole is isolated and the post-fault power transfer returns to 3 gigawatts. Note that the post-fault power transfer is the same as pre-fault due to the cross-trip of the 1 gigawatts of wind generation. That is, the amount of generation cross-tripped is equal to the initial power transfer on the faulty pole. The performance of the transient angle controller of the pole level control can be clearly observed in the negative pole of HVDC System 1. Initially, the converter begins to increase its active power absorption during the fault, causing the frequency order of the pole to increase. This is because the healthy pole can initially feed a large current to the DC fault since the offshore neutral point is ungrounded. The control loop quickly modulates the converter internal voltage angle based on the frequency error signal provided by the offshore frequency regulator. The change in internal angle causes a decrease in the active power absorption of the converter and lowers the frequency order. Next, we'll discuss some of the drawbacks of this proposed controller. The main con of this controller is that it is not autonomous. That is, it requires a fast master controller. Fast master controllers are generally not advisable because of the communication delay and risk of losing the communication channel. A test was performed to assess the sensitivity to the communication delay. In the figure, a 20 millisecond delay between the master controller and the pole level controllers of HVDC System 2 was introduced. The same AC fault that was shown in the previous slide was applied. The results show that the system is not sensitive to the communication delay since the differences in the terminal output is negligible. To mitigate the risk of losing the communication channel, a redundant channel would be necessary. So in summary, grid forming control for offshore HVDC systems is not a trivial task. We attempted to use many control strategies that are presented in the literature, but found that they were not able to maintain the offshore stability. There is certainly a need for VSC HVDC grid forming control, which is designed to operate in parallel for offshore wind collector systems. The unique characteristics of offshore grids and the parallel operation of tightly coupled converters pose unique challenges for grid forming control. A grid forming control concept is presented here, which uses a fast master controller to regulate the offshore frequency, and pole level controllers to define the converter's internal voltage magnitude and angle. Results of EMT simulations show that the control concept works quite well in regulating the offshore voltage and frequency and provides the support necessary to recover from faults. In terms of future work, HVDC grid forming control is an ongoing area of research at TGS. We're currently working towards a control scheme which eliminates the need for a master controller and which is designed to minimize steady state control interactions while also having a robust fault ride-through performance. Detailed EMT models as well as linearized small signal models are being developed to analyze these controllers. Thank you, and I'd be happy to discuss any questions that you might have.
All right, thank you so much, Riley. So let me see, I think I can unmute the attendees if they want to ask. And let's see, 1 second here. Okay, well, we have a question in the chat here, first of all.
Sure.
This is from Sam Maliki. Are the turbines in grid forming mode, or is it the HVDC converters that are in islanded mode, which control the frequency and voltage?
Yeah, it's the offshore HVDC converters in this study, which are forming the offshore AC grid. So they're regulating the AC voltage and frequency, and then the wind is in grid following mode.
Okay, Sam has another question. I unmuted you, Sam. I think.
Yeah, I think I have. Okay. Thank you so much, first of all, like for the presentation. It was a great thing. Just a quick question, like in terms of the difference between this grid forming mode of HVDC, how do you differentiate it between the grid forming an island and mode of HVDC, which is like a common practice, like so far?
So I don't know if I understand the question fully. So there were two parts to the study, the DC coupled hub and then the AC coupled hub. In the DC coupled hub, the AC side is it's decoupled on the AC side. So there's only one offshore HVDC converter, which is in grid forming mode, but it's islanded. So it's doesn't have to work or be a synchronous grid forming converter. Whereas in the AC coupled hub, all the offshore HVDC converters are connected to the same bus. So those ones have to be synchronous grid forming. I don't know, Sam, if I answered your question. If not, please.
So I can add a little bit more to this. Like,
sure. Yeah.
Like a typical offshore VSC HVDC needs to control the frequency and voltage, right? And it's been the practice so far. Now, how do you differentiate that between this new grid forming mode? Is there any difference, or is it the same thing?
No, it's the same. I mean, so this controller regulates the voltage and frequency.
Okay. Because at some point of the presentation, I noticed that you mentioned we are not controlling the frequency, but we are controlling the angle. And I was a little bit confused on that.
Okay, so in that part, all I was trying to point out is that in typical virtual synchronous machine controls, we control the angle through the frequency. But in this controller, there's a faster path that modulates the internal angle based on what the offshore frequency error is. So again, it's still between, it still controls the angle through the frequency, but there's a fast controller which directly modulates the angle. I don't know if that.
Okay.
Again, yeah.
Sure. No, I think, yeah, I got my answer. Thank you so much. Again, thanks for the presentation. Good stuff.
Thanks, Sam.
We got another question here. Spirios, did you want to unmute yourself and you can ask your question?
Yes, thank you very much for very interesting.
Sorry, Spirios, I think you're a bit low on the mic. Like maybe speak a bit louder.
Can you hear
Can't
me?
really hear. It's very
Hello?
faint. We can hear you, but it's very faint.
I don't know really.
Okay, that's better. That's better.
I shall try.
Yeah, that's good. We can hear you. Yeah.
Yeah. Yeah, thank you very much for the very interesting presentation. Actually, following Sam's question, I wanted to ask, yeah, there is obviously a differentiation between the islanded mode and the grid forming mode that this offshore converter could have. And my question is, when you're regulating voltage and frequency, obviously we talk about a PLL-less control offshore then, in order to separate it from the islanding mode of a typical VSC operation, isn't it?
Sorry, you said FPLS?
PLL-less, without PLL.
Okay, so sorry, I didn't quite get the question. Can you ask it again?
Yeah, if the offshore HVDC converter that you mentioned as grid forming, regulating voltage and frequency.
Yeah.
Okay. If it uses a PLL device.
It does not.
It does not. Yeah.
No, this does not use a PLL. You can show let's show the thing again. Yeah, so there's no PLL in here. The internal angle and the voltage magnitude are generated internally. Yeah.
Okay, because in many occasions the stability aspects could be formed, for example, because the short circuit ratio that is formed between the converter and the corresponding wind farm, depending also on the representation, can be in the range of 1, more or less. So weak grid conditions are being formed, and in that essence, you know that the dynamics can cause dynamic stability issues out of very small disturbances at the offshore system. And for example, in an equivalent case where a controller with PLL, like a typical vector current control system would be used, it would have plenty of issues at this condition. But having this kind of controller, probably we talk about a system that can have better stability margins at weak grid conditions that are needed.
Yeah, I agree. Yeah, agreed.
Okay, so if that's all from Spirios, we have is that all the questions you had, Spirios? I guess so. Yes.
Yes.
Okay.
Thank you.
Okay, so we have another question from Bruce. If you want to unmute yourself, you could ask it.
Hi, Riley. Thank you so much
Bruce.
for this presentation. I really learned a lot from you. Just have a question about the grid forming control that you mentioned for offshore wind farm application, because normally now if we talk about offshore wind farm, the reason to have the grid forming, because now people are using VF control. The reason is that people we want to provide a reference to start for the grid following wind farm, and I've also noticed that you mentioned that the grid forming that you mentioned is not in autonomous mode. But I'm just wondering that if it's not in autonomous mode, what's the why wouldn't we just use the VF? Then what's the advantage of this control compared with the VF, which is already mature in industry?
Yeah, so the reason that we need, so it's not autonomous because we have the master controller. And the need for the master controller arised out of recovering from transients. So that's where the transient angle controller mainly comes in to play. So this delta frequency error comes from that master controller, and then we can quickly, very fast, modulate the internal angle. And it helps us keep the stability during faults. So that is, I guess, the second part of the question. The first part refers to the wind being in grid forming. Correct, Bruce?
No, actually, I understand the wind farm is always in grid following because
Correct.
Yeah, because only the offshore HVDC converter is in grid forming mode, right?
That's right. Yeah, that's true. Yeah. So sorry, can you repeat the first part of your question?
No. Actually, my question was like, what's the advantage? Because you mentioned that the grid forming control that you're presenting is not in autonomous mode. So comparing with VF, which is already mature, because one of the advantage of using grid forming converter is that it can be in autonomous mode. That means if you want to maintain a frequency and voltage of AC bus, you can add as many as grid forming converter as possible, like theoretically, right?
Yeah, so our experience is that it's extremely difficult for many of the reasons that I've pointed out in this presentation, mainly due to control interactions between the parallel converters. It's very difficult to have good steady state and fault ride through performance for when you have parallel HVDC grid forming controllers.
Okay, thank you.
Yeah, thank you, Bruce.
Okay, so we have another question from Sam. If you want to
Yeah, it's an interesting topic. That's what I'm always jump in and ask questions. So just a quick thought on that one regarding the autonomous operation of these units. Have you tried like coordination of the droop settings for each control path, or did it work, or what do you think about that?
No, even with the droops equal, I assume that's what you mean with the coordination of the droop settings. So for all of these converters, the droop is equal at 5%. Even with
no,
that,
actually, I'm talking about not to have them at equal to to limit the interactions if you're seeing any adverse interactions. So usually you can like have some of them at like 5%, some at 10%, right?
Yeah, we did try, and again, lots of interactions was our experience with this. Yeah.
Interesting. Okay. Thank you so much.
Thanks.
All right, great. We have another question from Christian. If you wanted to unmute yourself, you can ask ahead.
Hi, Riley. Great presentation.
Hey, Christian.
Yeah, just a quick question for you. You know, you're talking about the difference between converters compared to the conventional synchronous machine, and one of the points you mentioned is this difference in the impedance that's presented to the AC system.
Yeah.
You know, you're talking about how the impedance presented by the converter is much lower than what we would typically see from the traditional synchronous machine. I'm not really sure if this will work or not, but you ever think about maybe trying to use some form of virtual impedance with the converter to try and introduce more, virtual impedance on the AC side of the converter? Just a thought. Maybe you can provide some comments.
Yeah, so this is, again, ongoing research going on here at TGS. So we are trying, and we're having some success with the virtual impedance method. Yeah, so it seems to allow us to get some electrical decoupling between the controlled node and the converter terminal, which really helps with interactions.
Yeah, I think like traditionally virtual impedance has been used in these grid forming converters as more of a current limiting technique to try and limit the voltage.
Exactly.
And by limiting the voltage, you limit how much current the converter can supply.
Yeah.
But in this case, it's not really for the same function here. We're just kind of trying to provide, like you said, more electrical distance or decoupling between. Try and make it look more like a synchronous machine, I guess.
Yeah, exactly. Yeah. Yes.
Okay, interesting work. Thank you very much for the presentation.
Yeah, thanks a lot.
So just to elaborate more on Christian's question, so if you were to incorporate that virtual impedance, would you get rid of the requirement for that master controller? Or would you still need that? Okay.
Potentially, yes. Yeah.
Okay, great. Okay, so we have another question from Bruce. Yeah, feel free to ask ahead. Yeah.
Sorry, I just heard the discussion between you and Sam about the PF droop factors of your control. You mentioned that the droop factor is 5%, is it?
That's correct. Yeah.
Have you ever tried to decrease the droop a little bit lower? That's say 1% or even 0.5%, because for the wind farm application, honestly, there is even no need to have like a frequency droop. You can probably just have a very little PF droop to adjust for like the power angle control, because that's related to your P and theta angle swing, right?
Yeah,
So because there is a paper that I recently just read that they mentioned that decreasing the percentage of PF droop may increase your control stability margin. Have you ever tried to decrease PF to a very small value? Do you still observe those control interactions between converters?
yes, yeah. So we tried droops across the board. I mean, reasonable droops, but we included small droops in this, even without the droop. And it was the same situation, that lots of interactions, yeah, between converters.
Okay, thanks.
Okay. I actually have one question. So for the onshore side, what was the strength of the system
Yeah,
when you tested this?
is that 3?
Oh, is that 3? Okay, so it's pretty weak. Okay.
Still a reasonable system strength, yeah.
Okay. Does anyone? Oh, we got another question. Oh, more questions.
I
Great.
have-
Great.
It's gonna be my last question. So I just want to like hear your thoughts about it. Like, do you think like there's a possibility that we can increase the stability of the system by having all the units on the grid forming mode? Because there are like several studies showing that for the AC system, grid forming inverter can increase the stability. So what if we have the HVDC in the grid forming mode, turbines in the grid forming mode, and somehow coordination, like have a better coordination just to strengthen the grid? Do you think there's a possibility? Is there any thoughts around that?
Yeah, so we tried this. Actually, in the reports you can read if you are interested in that. We did try putting some of the wind in grid forming as well. The main issue that we found, again, was the second order swing dynamics. And this goes back to this issue here. So during the fault recovery, we see this power swing. Since the HVDC converters are already operating near nominal, so they're sitting around 1 per unit steady states, and then all the wind is trying to, or experiences this power swing, it actually makes the situation worse in our experience. So the additional power pushes the converters into their current limits, and then because they're now acting as current sources, we end up losing stability in some instances.
Interesting. Okay.
All right, we have another question from Tuhin.
Hi, Riley. Thank you for
Hi,
the
Ben.
presentation. Yeah, and it was very interesting one. Just I want to learn something related to that contingency you have applied on a DC link. Can you go to that page?
Sure.
Yeah, in this case, there was a fault, pole to ground fault on HVDC system 1, positive pole cable. So in that case, I can see there is a huge reactive power absorption near to, if I assume that 1000 megawatt is 1 per unit, that's 3 per unit reactive power absorption. Can you specify that this is absorbed by converter or any other element?
It's going, so because the converter is faulted, this is going through the freewheeling diodes. So this is you can see the reactive power from the other converters is all up around 1000 megavar. And so this is syncing to the faulty converter through the freewheeling diodes and going to ground. That's the path that this is taking.
And it's actually going through the capacitors or just?
No, through the freewheeling diodes.
Okay, thank you.
All right, we have 2 minutes left. If anyone else wants to ask any last questions while we have Riley. Okay, great, great. So, thank you so much, Riley. Seeger Canada NGN is, very grateful for you for taking the time to do this presentation. It was a very good and a very interesting topic. Yeah, got some
Thanks for
claps
having
going
me.
there.
It
Yeah,
was great. Yeah.
yeah, thank you.
Really good.
And
And again, I would like to, anyone that would like to, I strongly encourage people to submit for that NGN sponsorship. It was a great opportunity. So yeah. And I guess we're
yes.
coming up to a Paris session here next year, right? So
Exactly. So that's a really good opportunity, the NGN sponsorship. We also have the NGN presentation showcase as well, if you are interested. If anyone's interested, feel free to reach out to me or even Riley. He understands this stuff too, so he can help you out. And if you need any hand on how to apply and all that, please feel free to reach out to any of us. Yeah, we'll be happy to help. Okay, great. Thank you so much. I think that's good for now. We can kind of end the webinar. So thanks, everyone.
Thanks. Thank you.
Thanks, Riley.